I will present ParqOpt, an Ingestion-layer file converter for analytical platforms. The problem is straightforward. Analytical systems receive heterogeneous input files, but conversion into columnar formats is not only a formatting task. The system must remain correct under retries, and partial failures, behave predictably across storage paths, and operate under explicit memory constraints. In this work, we contribute three things: an explicit S3 multi-part resume contract, a controlled evaluation of planner decisions under fixed ingestion semantics, and a split runtime with budget-aware streaming. Why is difficult in practice? First, the input data varies in format and structure. Second, object storage writes must survive retries and restarts without silent corruption. Third, streaming convention must stay controlled under memory pressure, especially for wide and string-heavy data. Fourth, writer settings affect both throughput and output size. These challenges define our three research questions. RQ1 is about correctness of multi-part resume. RQ2 is about planner quality under fixed semantics, including storage path and streaming budgets. RQ3 is about scalability of split runtime under load. This is the system structure. ParqOpt uses a split runtime with intake and execution separated into different planes. The control plane validates requests, stage input when needed, persists job state, and sends tasks to the queue. The worker plane executes the conversion job, runs the C++ pipeline core, and writes the result to object storage. This separation matters because it decouples fast requests admission from heavy execution and makes scaling behavior easier to study. Inside the pipeline core, data go through parsing, profiling, planing, and rewriting into Parquet or C or Avro. The streaming path is budget-aware. Data are processed as raw record batch streams, batch size is estimated online, and bounded queues provide back pressure. This gives a controlled execution under an explicit memory budget. The key claim here is deliberately modest. Streaming is not presented as a universal way to reduce absolute peak RSS. Its main value is controlled execution with explicit limits. Effects on peak RSS remain dataset dependent. RQ1 is about the S3 multi-part resume contract. On recovery, the system calls list parts, reconstructs confirmed parts and e-tags, recomputes confirmed uploaded volume, and checks that the next expected offset matches the volume exactly. This is important because resume is defined through explicit invariance rather than implicit behavior. If the offset does not match, the session is treated as desynchronized and the resume attempt is rejected. This makes correctness testable. RQ2 starts with planner. The planner uses profile features such as missing values, cardinality, repeatability, and strict characteristics. Based on the signals, it chooses target format and writer parameters. The main point is simple. Planner decisions are data dependent, especially for strings. That is why the paper evaluates them under fixed ingest semantics, so planner quality is measured without mixing it with unrelated pipeline differences. This slide shows the experimental design. We used three workload classes: typical, high cardinality, and Y-string heavy. The main compositions cover local versus S3 compatible storage, automatic planner versus fixed defaults, stream on versus stream off, and different runtime configurations. The baseline matrix ran on the 8 CPU, 32GB VM, but Final paper also includes supplementary confirmation runs on object storage at 1 and 5 GB and local confirmation runs at 20 GB. This addition improves confidence, although they do not replace a dedicated distributed S3 evaluation. Here are the main correctness results. For the Q assumed, the S3 multipart resume path passed 11 out of 11 checks. The local target passed 10 out of 11, so one local append resume limitation remains. The important clarification is that the gap is confined to the local append resume pass. It does not affect the evaluated S3 multipart resume contract. The same slide also shows that S3 is slower than local, roughly by factor of 3 to 4, which consistent with staging and commit overheads. This is the main RQ2 result slide. On the left, the automatic planner is compared with fixed defaults under matched internal conditions. The planner improves output size in all 6 matched compassions. On the right, streaming is evaluated across 48 matched pairs. The result is mixed but informative. Streaming reduced max RSS in some cases and increased it in others, while throughput improved in many compassions. So the conclusion is careful. The planner clearly helps on output size and streaming provides budget-aware execution with bounded queues, but effects on absolute peak RSS remain dataset dependent. RQ3 is about scalability. Completion P95 improves as we add workers when the worker plane is a bottleneck. In the metric, the best completion P95 is achieved with 1 control plane replica and 8 workers. The soak test shows the main limitation of the current implementation. Out of 700 requests, 696 were accepted and 4 were rejected. All 4 rejections were caused by SQLite single writer contention. So the split runtime scales on the worker side, but the current job store backend limits concurrency. To conclude, RQ1 received a clear positive answer. ParqOpt makes multi-part resume explicit and testable through a concert S3 contract and deterministic QA checks. RQ2 receives a qualified positive answer. The planner improves output size under fixed ingest semantics, and streaming provides an explicit memory budget and bounded queues. But absolute peaks RSS is still dataset dependent. RQ3 also received a positive answer with a caveat. The split runtime improves completion behavior as worker parallelism increases, but SQLite constrains concurrency under load. Overall, ParqOpt combines a testable resume contract, controlled budget-aware streaming and split runtime with measurable scaling properties while remaining explicit about current limitation. Thank you.